we have seen the distributions of several random variables. Many times we are not interested in the original random variable itself, but certain function of it. For example, sums of random variables or say difference or any linear function of those random variables. So, in general, if I have a measurable function of random vector x 1 x 2 x n, then it will also be a random variable. So, we state it in the form of following theorem: let f from say R n to R m be a measurable function. So, if x is equal to say x 1 x 2 x n is a random vector, then let us call it say y is equal to f x is also a random vector. This is so because random variable x is a measurable function from omega n to R n, and a measurable function of a measurable function is measurable function. So, y becomes a measurable function from basically omega into R m. So, this is measurable, and so this is a random vector. So, now the methods of determining the distribution of y. So, one is the Mgf approach. We have already seen application of this approach in determining distributions of sums of certain random variables. So, if we are having certain independent random variables and we want the distribution of the sum, then it is the distribution, it is the product of the individual Mgfs, and in many cases where the Mgf, the product of the Mgfs can be determined in an explicit form as an identifiable Mgf, then the distribution of the sum can be determined. It can also be used for distribution of difference etcetera, where the forms are well defined. In the case of discrete distributions or in certain other cases where the CDF can be directly used, then we can use directly the CDF or the probability mass function. Let me give an example of this. Suppose x and y are independent and identically distributed binomial n p variables. Okay, suppose we want the distribution of u, that is x plus y, then from Mgf approach we are able to determine it is binomial 2 n p. Now, suppose we want the distribution of say v, that is x minus y, then let us look at the set of values of v. This will vary from minus n minus 1 minus 1 0 1 2 up to n, because each of x and y can take values 0 1 to n. So, probability of v is equal to say small v, that is probability of x minus y is equal to v. This we can write as x minus is equal to v plus y. Now, y can take values using a binomial distribution n p. So, we can use the theorem of total probability here and write it as probability x is equal to say v plus y into probability of y is equal to y. This is because of independence I can split for y is equal to 0 to n. Now, this is subject to the condition that v plus y is also lying between 0 to n. So, this is equal to n c v plus y p to the power v plus y 1 minus p to the power n minus v minus y n c y p to the power y into 1 minus p to the power n minus y. So, this is equal to sigma n c v plus y n c y p to the power v plus 2 y and 1 minus p to the power 2n minus v minus 2y, where y is equal to 0 to n, subject to the condition that v plus y is also taking values 0, 1 to n, because v plus y denotes the value of the random variable x here. So, this shows that in the case of discrete random variables, directly the probability mass function can be used to determine the distribution of a function. Let us take another case here. Suppose I define, say, u is equal to x by y plus 1 and v is equal to, say, y plus 1. I want the joint distribution of u and v here, where x and y follow independent binomials. So, here you look at the set of values, v will follow, since y is binomial n p, y takes values 0, 1 to n. So, v will take values 1, 2 up to n plus 1, whereas the values of u will be, now here x can take value 0, x can take value 1, in that case y plus 1 can take values all these. So, 1, 1 by 2, 1 by 3 and so on, 1 by n plus 1. X can take value, say, 2. So, these values can be 2, 2 by 2, 2 by 3 and so on up to 2 by n plus 1 and so on, n, n by 2 and so on, n by n plus 1. So, these are the possible values taken by u. So, we look at probability of, say, u is equal to small u, v is equal to small v, where small u and small v take these values. Then this can be expressed as probability x is equal to u v and y is equal to v minus 1. So, x and y are independently distributed. So, this becomes product of that is equal to n c u v p to the power u v 1 minus p to the power n minus u v, then n c v minus 1 p to the power v minus 1 1 minus p to the power n minus v plus 1. So, this is the joint distribution of u and v, where u and v take these values. Let us take another example here. Say x and y have the joint mass function. The probabilities are 1 by 6, 1 by 12, 1 by 6, 1 by 6, 1 by 12, 1 by 6, 1 by 12, 0 and 1 by 12. So, x takes values minus 1, 0 and 1 and y takes values minus 2, 1 and 2. Suppose I define u is equal to modulus of x and v as y square. Then the possible values of u are 0 and 1 and possible values of y are v are 1 and 4. So, the joint distribution, that is probability, say u is equal to 0, v is equal to 1. That is simply probability of x y equal to 0, 1, that is 1 by 12. If we look at what is the probability of u is equal to 0, v is equal to 4, it is the sum of x is equal to 0, y is equal to minus 2 plus probability x equal to 0, y is equal to plus 2. So, if we add these probabilities, we get 1 by 12. In a similar way, we can obtain probability of u is equal to 1, v is equal to 1, u is equal to 1, v is equal to 4, and the joint distribution turns out to be, we can express it as u v. U can take values 0 and 1, v can take value 1 and 4. So, the distribution is the 0 1 is 1 by 12, 0 4 is 1 by 12, 1 1 is 1 by 3 and this is half. And from here we can derive the marginal distributions of u and v. So, in the case of discrete distributions etcetera, it is possible to derive the distribution of the function of random variables by directly considering the probability mass function. Sometimes it is easy to use the direct cumulative distribution function also. I can give an example here. Let us consider, say, let x and y have joint probability density function, say f x y, given by 1 plus x y by 4, where modulus x is less than 1 and modulus y is less than 1, 0 elsewhere. So, we want, say, the distribution of u is equal to x square and v is equal to y square. Let us consider, say, CDF of u and v, that is probability of u less than or equal to small u, v less than or equal to small v. Now, notice here that both x and y lie between -1 to 1. So, here the valid region for u and v will be between 0 and 1. So, we consider that 0 less than u less than 1 and 0 less than v less than 1. So, for this case, this is nothing but probability of x lying between minus root u to plus root u and y lying between minus root v to plus root v. So, this is nothing but the integration of the joint density over this region. So, that is integral 1 plus x y by 4 dx dy over minus root u to plus root u minus root v to plus root v, and we can evaluate it to be root u root v. So, the joint CDF can be obtained. From here we can determine the density of u and v. In general cases, when we have continuous random variables and we make a transformation of that, it may not be so easy to look at the joint CDF etcetera. In that case, like in the case of univariate random variables, we have an approach, the so called Jacobian approach for determining the distributions of random variables. So, we state it in the form of the following theorem. Let x 1, x 2, x n be an n dimensional continuous random vector with joint probability density function, say f x x. So, here x is denoting the vector x 1 x 2 x n, small x is denoting the vector x 1 x 2 x n. Let u I is equal to g I of x, I is equal to 1 to n, be a 1 to 1 transformation of R n to R n. Okay. That is, if I am taking 1 to 1, then there exists inverse transformations . Let us call it, say, x 1 is equal to, say, h 1 of u and so on, x n is equal to h n of u, where u is u 1 u 2 u n defined over the range of transformation. Let us assume that the mapping and the inverse are both continuous. Further, assume that the partial derivatives del x I over del u j for I j is equal to 1 to n, that is all partial derivatives del x 1 by del u 1, del x 1 by del u 2, del x n by del u 3 and so on, all the partial derivatives exist and are continuous. Then we define, assume that the Jacobian J of transformations which is defined by J is equal to del x 1 by del u 1, del x 1 by del u 2 and so on, del x 1 over del u n and so on, del x n over del u 1 and so on, del x n over del u n. Assume that this Jacobian does not vanish in the range of transformation. Then the random vector u is equal to u 1, u 2, u n is continuous and has joint PDF given by, so we write it as f u is equal to f x. Now, in place of x 1 x 2 x n, replace it by h 1 u, h 2 u, h n u multiplied by the absolute value of the Jacobian over the range of the transformation. If you see it carefully, it is a straightforward generalization of the result for one dimensional case. In the one dimensional case, we had considered a 1-to-1 transformation and we had looked at the dx by dy term. So, the density of the transformed variable was obtained as the density evaluated at x equal to g inverse y multiplied by the absolute value of dx by dy term. So, when we have a n dimensional random vector and an n dimensional transformation. So, if it is a 1-to-1 case, we look at exactly the inverse function and calculate the determinant of the partial derivatives, call it Jacobian, substitute the values of x 1, x 2, x n in terms of u i's and multiply by the Jacobian term, absolute value of the Jacobian, that yields the joint density function of the transformed random vector. So, let us look at a few applications here. Let x 1, x 2, x 3 follow exponential with lambda is equal to 1. Suppose they are independent and identically distributed random variables. Let me define y 1 is equal to say x 1 plus x 2 plus x 3, y 2 is equal to say x 1 plus x 2 divided by x 1 plus x 2 plus x 3 and y 3 is equal to say x 1 by x 1 plus x 2. We are interested in the joint and marginal distributions of y 1, y 2 and y 3. Of course, here if we are interested only in a distribution of y 1, then that is directly obtained, because the sums of independent exponentials is a gamma. So, y 1 will follow a gamma distribution with parameters 3 and 1. So, that is directly known. However, that does not yield the distribution of y 2 or y 3. So, we observe here that it is a 1-to-1 transformation and inverse functions can be written as x 1 is equal to y1, y2, y3. x2 can be written as then y1, y2 into 1 minus y3, and x3 can be written as y1 into 1 minus y2. So, we can determine the Jacobian of the transformation. Dou x1 by dou y1 is y2, y3, dou x1 by dou y2 is y1, y3, and so on. y2 into 1 minus y3, y1 into 1 minus y3, minus y1, y2, 1 minus y2, minus y1 and 0. So, if we evaluate this, it turns out to be minus y1 square y2. So, the firstly we write down the joint density function of x1, x2, x3. So, the joint PDF of x1, x2, x3. So, since x1, x2, x3 are independently distributed, the joint density is nothing but the product of the individual density functions of x1, x2, x3. It is product of f x I, that is equal to e to the power minus sigma x I. Each x I is positive. Therefore, the joint density of y1, y2, y3 can be obtained from here by substituting the inverse functions of x1, x2, x3 and the corresponding range and multiply by the Jacobian. So, the joint PDF of y is equal to y1, y2, y3 is f e to the power minus y1 into y1 square y2. The range of the variables we can observe here, that each of the x i's is a positive random variable. So, each of y i's is also a positive random variable. Further, if x 2 is positive, then y 3 will be less than 1, and similarly y 2 will also be less than 1. So, the ranges are y 1 greater than 0, y 2 and y 3, they belong to the interval 0 to 1. So, we have been able to determine the joint distribution of y 1, y 2, y 3. In order to get the marginal distributions, we notice here that if we integrate with respect to y 3 from 0 to 1, we get the same term. And therefore, if we integrate this with respect to y 1, y 2, it should give the density of y 3 as 1 on the interval 0 to 1. So, the marginal distributions, the marginal densities of y 1, y 2 and y 3 are obtained as f y 1 as half y 1 square e to the power minus y 1, which is nothing but a gamma distribution with parameters 3 and 1. F y 2 is 2 y 2 for y 2 between 0 and 1, and f y 3 is equal to 1 between 0 and 1. So, this is a uniform distribution. One interesting feature we can notice here, that if I look at the product of the marginals, it is equal to the joint. Note that f of y is equal to the product of so y 1, y 2, y 3 are independent. So, here we are able to obtain the distribution of a 3 dimensional function of 3 random variables here. The important thing to notice here is that apart from substitution in the density function and multiplying by the Jacobian, we have to also judiciously determine the ranges of the variable. Like one may simply say that y 1 is positive, y 2 is positive, y 3 is positive, without noticing that y 2 and y 3 are less than 1 also. In that case, if we will evaluate the integrals of this density, it will not give us 1. So, that will be not determining the density correctly. Let us take uniform distributions. Let x and y be independent and identically distributed uniform random variables. Let us define, say, u is equal to x plus y and v is equal to, say, x minus y. Now, clearly this is a one-to-one transformation. X is equal to u plus v by 2 and y is equal to u minus v by 2. So, if we look at the Jacobian term, dou x by dou u is half, half, half and minus half, which is equal to minus half. So, the joint PDF of, say, x and y, that is f x y, it is the product of the individual distributions of x and y, both are uniform 0 1. So, it is simply 1 for 0 less than x y less than 1 and 0 elsewhere. So, the joint PDF of u and v is it will become half for 0 less than u plus v less than 2, 0 less than u minus v less than 2. Now, the ranges of u and v, we can notice further here that since x and y are between 0 to 1, u will be between 0 and 2 and v will be between minus 1 and 1. This gives the joint density function of u and v. Suppose we are interested in the marginal distributions of u and v. So, in order to get the marginal distribution of u, we need to integrate this with respect to the variable v. So, the marginal density of u is obtained as, so, f u integral of this joint density, that is half d v. Now, notice here the range of v. V's absolute range is from minus 1 to 1, but here v lies between minus u to 2 minus u and v is less than u and v is also greater than u minus 2. So, if we determine the region, it is from minus u to u if u is between 0 to 1, it will be half u minus 2 to 2 minus u d v if v is between 1 and 2 and 0 elsewhere. So, after simplification, this turns out to be u for 0 less than u less than or equal to 1, it is 2 minus u for 1 less than u less than 2 and 0 elsewhere. Notice here this is a triangular distribution 0 to 1 and 1 to 2. So, the distribution of the sums of two independent uniform random variables is actually a triangular distribution. In a similar way, we can obtain the marginal density of V also if we integrate with respect to u. In a similar way, the marginal PDF of V is obtained as FVV. It is integral of half with respect to u from minus V to V plus 2 for minus 1 less than V less than or equal to 0. It is half from V to 2 minus V du for 0 less than V less than 1 and 0 elsewhere. So, after simplification, this turns out to be 1 plus V for minus 1 less than V less than or equal to 0 and 1 minus V for 0 less than V less than 1, 0 elsewhere. This is again a triangular distribution on the interval minus 1 to 1. So, minus 1 to 0, the density is 1 plus V, and between 0 to 1 the density is 1 minus V. So, we notice here that the sums and differences of independent uniform random variables are again triangular distributions, and obviously, they are not independently distributed here, because the joint distribution of u and v is not equal to the product of marginal distributions of u and v here. Now, in many cases, the function from R n to R n need not be 1 to 1. For example, we have considered the discrete case where u was modulus x and v was y square. So, it is not a 1 to 1 transformation, rather it is a 4 to 1 transformation over the range of the variables. So, in that case we have a result similar to the case of univariate. In the case of univariate, when we had a many one transformation, we split the domain into disjoint regions such that from each region to the range we have a 1 to 1 transformation. We consider the inverse transformation. Using that, we calculate the density function in each region of the domain, disjoint regions, and we add all of these. That gives the joint distribution. So, a generalization of this result is available for the n dimensional case also, and we state it in the form of the following theorem. Let x is equal to x 1, x 2, x n be a continuous random vector with joint PDF f of x, and let u be a mapping from R n into R n, where u is equal to u 1, u 2, u n, u I is equal to some g I of x for I is equal to 1 to n. So, we are not assuming that it is a 1 1 on 2 function. Suppose that for each u the transformation g, that is g 1, g 2, g n, has a finite number, say k, of inverses. Suppose further that R n can be partitioned into k disjoint sets, say A1, A2, AK, such that transformation G from AI into Rn is 1 to 1 with inverse transformation say x1 is equal to h1 I u and so on, x n is equal to h n I u for I is equal to 1 to k. As in the case of previous theorem, we have to assume that the mapping and in the inverses are continuous, and this first partial derivatives are continuous. Suppose that first order partial derivatives are continuous and each Jacobian, that is Ji, that is del h1 I by del u1 and so on, del h1 I over del un and so on, del h n I over del u1 and so on, del h n I over del un does not vanish in the range of transformations. Then the joint PDF of u is equal to u1 u2 un is given by f u is equal to sigma f of x h 1 I u and so on h n I u multiplied by absolute value of the Jacobian I is equal to 1 to k. So, note here, if we consider this term, it is the density determined by the 1 to 1 transformation from A I into R n. So, we calculate this density for each region A 1, A 2, A k and add. This gives the joint distribution of u 1, u 2, u n. We consider an example. For example, we can consider distribution of order statistics. Thank you.